Everybody.
Good evening, sir.
Did you done what we have covered in previous class? Any problem, any doubt in the previous class? Okay, then I assume that you don't have any doubt. So, okay. Hmm. So, in the previous lecture, we have covered the basic definition of probability space and also covered some properties that is related to probability theory. So today we are going to discuss some further properties of the probability space that is important in the study of statistics, and also we will also cover some questions that related to your exam. Okay. So let me see. So, so first we do a very simple question. Mm, okay. I hope this is visible to everybody.
Yes, sir.
So, did anybody try that previous year questions of the statistics? Like some of the questions are very, very basics and very easy. Actually, you can solve those questions by just layman approach. Layman approach, I mean to say, if you don't understand the advanced notion or the definition of, statistics, still you can solve those questions. And there are always 5 to 10 questions are these kinds where you don't require, deep understanding or very much understanding of any topic. You just have to understand the question and you will able to cope up that. So, for example, this is a question number, this 61. Okay, did anybody try this question? Okay. So the question is if the arithmetic mean of 10 number is equal to 12 and two of the numbers 12 and 18 are removed and replaced by 20 and 30, what is the arithmetic mean of new set of 10 numbers equal to? Okay, next time I will prepare a PPT properly so that these kinds of disturbance will not happen. Okay, so anybody would like to try this question? Okay, we will do this question. Okay, this is fine, right? So okay, so if the arithmetic mean of 10 numbers is equal to 12 and two of the numbers 12 and 18 are removed and replaced by 20 and 30, what is the arithmetic mean of new set of 10 numbers equal to? For example, we have x1, x2, x10. These are 10 numbers. What is the condition is given? That their arithmetic mean is given to be 12. Means x1 plus x2 dot 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 x10. Their arithmetic mean is, I hope this is the basic formula I am using. So how to calculate the mean, arithmetic mean, what we say arithmetic mean, what is the total sum of the quantities divided by the number of quantities, that is the average mean. There are so many names. No doubt we will see the definition of this arithmetic mean by axiomatic definition of probability as well. Okay, that's a you know further talk. So now it is given to be 12. It is given to be 12. So you can see that how it is 12, that the sum of the numerator, it would be 120, then that is the only possibility 12 is coming. It means the sum of these numbers is coming to be 12, or you can simply multiply this denominator to right hand side and you will get 120. But if the condition is given that 12 and 18 are removed, 12 and 18 removed, it means what? If I,
What? Sum
okay,
is 90 now.
uh, what sum is? The
90.
sum is
120 minus 30, sum is becomes 90 now.
okay, okay, okay. That is 90. Sum is become 90. Okay. And replaced by 20 and 30, and it means 20 and 30 we have added to them. That is one.
That's
That is 50.
140. Plus 50.
Okay. So okay. So the sum of the numbers of the these 10 numbers we come to be 140, and divided by 10, that is 40.
Okay.
Okay. So that's a very simple question. Okay. So this is the question. Okay, in this question, you don't require any much information of any statistics, probability, or whatever you study in your mathematics. Now let's do. Okay, so one question we will do, and then we will go back to the theory. Okay, this question, that question number 17 we will see. Say, if A and B are any two arbitrary events in a probability space, which of the following is not true? Okay, so first of all, we have to understand the question. What is A and B are any two arbitrary events? So I feel that we have discussed very much about the what is the events in a probability space, and conditions is given. Conditions is given. This condition is given. Uh, you have seen that probability. Okay, that is here. Probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. By this formula, you can easily do this question. Okay, so the question comes that these are the 7 to 8 formulas are there in probability theory. that we have to know from where they came and why they are why they are true. So by this formula, you will able to do easily this question. Okay, we will return to this question after uh, cover some theory. Let's do first. Okay, so this is just a, we can say that A and B are any two arbitrary events in the probability space is given, and the relations of the union of their and some of the probabilities asking what will be the true and from this you can see that probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. This is given, but here this formula, this C option, this is false. Clearly you can see. And why this formula is coming and why the other formulas are true, let's see the basic theory. Okay, so now let me share the, okay. So everybody can see the whiteboard. I hope everybody can see. Okay, we will do some more questions today as well. Ultimately, we have to solve the question in the exam. Okay, so yesterday I have covered some theory on the basic definition of probability. Basic definition of probability. I have defined the omega as a sample space. F script F. I would say that is script F. Script F as the event space where total uh, power set of the omega, and no, this is P, and this P is different. This is P is a probability function. That probability function I have defined from script F2, close interval 0, 1, that three axioms are satisfied by this function. And we have done some properties as well, that three axioms that is satisfies. And afterward, we have seen that probability of phi is 0, and if there are disjoint subsets or disjoint event, then uh, say EIs, and I belongs to say natural number. It may be finite, infinite. I mean to say countably infinite. Then probability of, this is important property, is union I, that I can write as sum of the probability of EI. The condition is, we know very well that EI intersection is phi for all I not equal to j. Whenever I not equal to j, it should be empty. So now if I say that let A is a event, B is a event. What is mean by event? That this belongs to script F. What is script F? That is power set of omega. And the what is omega? That is a sample space. That is a sample space. Whenever you have a problem in understanding, you just associate this theory to the most basic example. For example, you can associate with the dice, with the throwing of a coin, and eventually you will understand the concept, and then you can generalize this concept to any experiment, any random observation. Okay, so AB is belongs to script F, and what is the condition? That A is a subset of B. So then I will able to write that B is equals to A union. This is A complement intersection B. Okay, so if this is a Venn diagram, just two understanding for this. If this is A, this is a B. Okay, A is a subset of B. Okay, if this is A, this is B. Okay, so A is a subset of B, and this is whole probability space. Then you can say that B is, what is B? This is A union. This is A union. This A complement intersection B, and you can see that these two sets are disjoint. If these two sets are disjoint, and if I apply the set theory, then this is probability of A union A complement intersection B, and by the probability law, I can write the right hand side as the probability of A plus probability of A complement intersection B. So this is also an event. This is also an event. So if you know that that's a basic understanding that this is greater than zero. This is always greater than zero because we have defined the probability function in this manner. If I add probability of a both sides, then this is greater than probability of a. It means this right hand side is this is okay. So this is okay. This inequality is holding this probability of a, or I can say that probability of b is greater than probability of a. But I have taken that if A is subset of B, then probability of A will be less than probability of B. So you have to keep in your mind clear that this is the sets. So I am using the notation A subset of B, and these are the real numbers. So I am using inequality that Krishnamurti law. It means the probability of A is greater than, less than, or equals to those. These are the numbers. Okay, so this is known as, but I can say monotonicity. Okay, but more is right. Okay, so if I have an event A, this is the event, this is the event B, this is the event B, and this is my whole sample space. Oh, event space. Sorry, this is not a sample space. This is event space. This is my script F because A and B are the events. And okay, so this is, if I say that what is A union B, I can write it as this portion, union this portion, union this portion. Okay. So what is this first portion? This is, I say this is the first portion. So this first portion is what? A
A.
intersection. Okay. Anybody want to tell that B complement, right? Is it right? And the second portion, this is the second portion intersection B. And the third portion is this one. So this I can write as A complement intersection B. So to convince yourself that this is the right thing, whatever I have write it here. So just check. So you can see that if I apply the probability function, so you can ask that this is the sets. I'm taking the sets. So why I can apply the probability function? So this is the property of the function, that if I have some subsets of the domain, then I can apply the function. They are equal like this. So A union B is equal like this. So I am just applying that P. If I apply the P, for example, if I say this is X, this set is Y, this set is Z. Okay, so this is X union Y union Z. And you can see clearly that this set, all three are disjoint, pairwise, whatever two sets you take, they are disjoint. So you can write easily that probability of X plus probability of Y plus probability of Z. Okay. So intersection B complement plus what is Y, probability of A intersection B, probability of A complement intersection B. Okay. So hmm. Okay. So now what is A intersection B complement? A intersection B, I can say that this is no A, this whole part, this whole part A intersection B, intersection B. Okay, should I use that notation that A minus B? Okay, B complement. Okay, this is same. Okay. Without using that notation, how can I write? Okay, so what is A here? What is A here? A is simply A intersection B union A intersection B complement. This is fine. Okay. So here I can apply the probability. Okay. Anybody have doubt? Any doubt? Okay. So these A intersection B. Okay. This is the A intersection B second part and A intersection B complement. So this first part, these are the disjoint and this is equal to A when I do their union. So I'm just applying that probability function is intersection B complement. Simply I'm writing it here. So I can write it as from that right hand side A intersection B complement as probability of A. This. So this is the equation first and if I take some, you know, how to say the color. Okay. And if I take B, what is the B? B is simply A intersection B union that second part and the third part. What is the third part? That is A complement intersection A probability of B. So okay, so if you have any doubt, then please ask the doubt, and if you don't have, please put your mic on. Am I audible to everybody?
Yes, sir.
Okay. Then these are the joint, and I can write it as A intersection B. So so from here I can write it as also this part you can take as probability of B minus probability of A intersection B. That is simply equal to that this right hand side, this intersection part I have taken to this left hand side and this A complement intersection B. So this is the equation number 2. So if this is the equation number, if this is the equation star, then what I can write? This hmm, okay. So I am just putting this equation. This is the A intersection B complement. This is A com, uh, A intersection B complement. I am putting the value here and the second value is here. So what I will get? So so I am put values. Okay. So what I will get? That this is left hand side. What is P A union B? That is simply probability of A minus A intersection B. This is probability of A intersection B as it is. Remember, these are the real numbers, right? So, and in the third term, P A complement intersection B is given to by this second equation. That I'm just putting the value. That is probability of B minus probability of A intersection. That is the thing. Okay. Okay, so you can see that the probability of A intersection B and this is cancelled out, and the remaining part is this. This is this remaining is this remaining, this remaining, and this remaining. You can see that on the left hand side this is the one, and on the right hand side these are the three terms that are remaining. So I am just writing down those three terms as okay. So when I write that, then I can write probability of A union B is probability of A plus probability of B minus probability of A intersection B. So these are the only things. Okay. So, so this is a way. Okay. So why I can write this? So this is known as inclusion. exclusion principle that we are using since earlier classes, and by the axiomatic definition of probability, we have also derived it. So this is known as inclusion exclusion principle. So from here you can see that one observation, just a note. Okay, you can see this is a note. Probability of A union B, the probability of A intersection B, that is probability of A. Okay, so this, so since we know that A intersection B is an event and every event has probability that is greater than zero, so I can write probability of A union B, that is less than probability of A plus probability of B. So this is the right way to make a connection between individual probability and their unions, and I hope you see that question. That's the question. Okay. Mm, okay. So this is the question, right? This question is easy to handle now. So you can say that probability of A union B less than equal to that we have derived. We just derived it. Okay. So probability of A intersection B is less than equal to probability of A plus probability of B. So we know that A intersection B is less than sorry, is subset of A. And we just have derived that if A is a subset of B, then probability of A less than equal to probability of B. That monotonicity law at the initial we have derived then probability of A. So this property is holding because probability of B is always positive. So you can see that C part is not there. We didn't see any these kinds of equality. And probability of A intersection B is less than probability of A less comma probability of B. It's a minimum, right? So you can say that A intersection B subset of A, then probability of A intersection B is less than equals to probability of A. Similarly, A intersection B is subset of B. So we will easily see that probability of A intersection B less than probability of B. It means that if a number is less than two numbers, then the number itself is less than minimum of the two numbers. So this also holds true. So easily we can. So we have two ways to see this, that either you terminate the three option, or you just cover. Okay, so this is one. So now let me share that. Okay, so now we this is known as ban from inequality. Ban from inequality. I'm just giving you the name. By chance, if you see their names, you shouldn't be get afraid that who they are, what they are like. Okay. So this we have done. So now let's go to some. Okay, we have discussed omega, right? We have discussed omega. What is omega? What is omega? Okay, anybody want to tell? We are discussing omega since first.
Sample space.
Sample space.
Okay, so sample space can be countable, uncountable, and in countable there are two
Infinite.
countable there are two possibilities: finite and infinite. Okay, So there are so many definitions of countable. It means there are some, some authors use countable as, only for finite, only for finite set, and infinitely countable. That means the set is infinite but is countable. And the third term is uncountable. That omega can be countable. It can be infinitely countable. And the third one is uncountable. Okay, so I have given an example, right? So now let's see that why we require that. Okay, it will be a only, little bit exposure. Why we study these kinds of, why we need the axiomatic probability. Why we need the axiomatic probability. For example, whenever you are throwing a dice, you have possibility 1, 2, 3, 4, 5, 6. Any number can come. So what you are doing? What is the probability of coming one? That is 1/6. That what you are doing? You actually doing distributing, or you are assigning probability to each number equally. That is equally likely to happen. Okay, if I say that omega is your, 1, 2, 3, 4, and so on, this is a set of natural number, I can say. If I want to assign them probability equally likely, okay, equally likely, then what will be the probability of omega? Okay, it should be one, right? It should be one. And and then I can say that probability of any, I will say that any alpha, and alpha belongs to natural number. Say, right? Probability of 1, probability of 2, that alpha belongs to natural number, that should be 1 because it is covering whole sample space, right? It means what? It means what? If the sum of a series is convergent, what does it mean? That limit that n tending to infinity, probability of n, that will be 0. That I feel that you know this result, that if a series is convergent, some finite number, then limit n tends to infinity, then its tail is going to be 0. It means what? As we are going to infinity, what is the condition of probability? The condition of probability is that every event has probability greater than 0. Okay. But this is saying that the tail of that sequence is going to be 0. Huh? The tail is going to, no, actually, if we are taking this, this is to be the sample space, then at every point we need probability greater than equal to, strictly greater than 0. That's the definition of that domain, because we are considering 1, 2, 3. Whenever we throw a dice, we are considering the sample space as 1, 2, 3, 4, 5, 6. We are not considering 7. If you consider in 7, why you are not considering 7? Because 7 has probability 0. In omega, you consider only those points which have some positive probability, Okay. So let me clarify the one fact that when you consider an uncountable set, it's not compulsory to have probability positive at every point, but whenever you are defining infinite countable or countable set as omega, then every point have some positive probability. So here I have defined this omega as set of natural number, and each natural number required positive probability. So here it is saying that as n tending to infinity, this is going to be 0, but I required that Pn should be greater than 0, strictly greater than 0. So this contradiction is coming on the fact. Why it is contradiction is coming? Because I try to assign probability equally likely on each number. So we cannot assign probability equally likely when we have these kinds of set as omega. Okay, so axiomatic definition of probability will help us. Then how to deal with these kinds of data? When there is a countable, it means there is a finite set, easily we can define, equally likely probability. There is no harm. There is not required to define equally likely probability. It means we have done that previous class question. We have defined that probability of head, that is p, and that probability of tail is 1 minus p, and p is just greater than 0 and less than 1. Okay, so but we have defined, it is not compulsory to define equally likely, but in finite it is sure that we can define equally likely. For example, for the set of natural number, if anybody wants to define, I'm not going very deep in this example. We'll tell you that if this is the omega, this is the omega, this is the set of natural number, and you define probability at each point. Okay, the probability we can define here. Okay, probability on any number that is 1 by 2n. Okay, for example, at probability at 5, what will be the probability at 5? 2 to the power 5. And whenever you will see that this is a p is a function, you know that is f2 close interval 0 1, and this f is somehow complicated in itself, but we don't require that that much information. It is a power set of natural number. This is a power set of natural number. I hope you have studied this power set of natural number, but it's not very much required. You just keep in your mind that this omega is a set of natural number, and f is the even space. It means every subset of natural number we are taking, and I'm just defining this, and it will satisfy that those three axioms, 1, 2, and 3. You know that the axioms that power set of probability of omega is 1, probability at any event is positive, you can see, and that sequence disjoint probability will be equal to the sum of the union. That 3 you can easily see, and it will define a probability function. Okay, so you just check by yourself. If you have any doubt, we'll talk about this. Okay, so there is a definition of fair as also given. If a coin or a dice or any experiment that have equally likely probability of every event, then we will say it is a fair. Like if I throw a fair coin, it means probability of head and probability of tail will be equal. Okay. Fairness means whenever we are tossing uh, for a match, why we are tossing the coin only? Because we know that this is fair. Because fair means this is not biased. It's not inclined on any toward any team. So that property you can see that we use. Okay. So I'm sending the notes as well. So I'm just I'm trying to make a ladder. So whenever we have some shortage in the ladder, we'll try to put the information to fill the hole. Okay, so I'm sending the notes also. You just try to cover it because these concepts are always useful, but these concepts are important. You have to study to answer the questions in the exam. I understand that questions are not very much, on the deeper level, but at least you have to understand them. And, and for understanding, you have to study. Okay. So one more thing that we have done. That's just a note. That's just a simple note that we have done probability of A union B. That is probability of A plus probability of B minus probability of A intersection B, and you can extend this version as probability of A union B union C as right probability of A plus probability of B plus probability of C minus probability of A intersection B and B intersection C minus probability of A intersection C and the plus probability of A intersection B intersection C. And your homework, or you can say this is a task that this we have derived in class. You try to derive this formula from this formula, and then you have to use that PMI, that principle of mathematical induction, that this inequality can be generalized to any number. It means on the whole natural number. I feel that you know that what is the PMI. Okay, in graduation or in the masters we have done these kinds of inequalities. Okay, so these are known as inclusion exclusion principles. I have already told you that this is also inclusion exclusion principle. So if you feel any doubt, you're free to contact. Okay, so sometimes it happens that when we are performing some experiment, it is quite possible that whatever previously outcome has done, will affect the upcoming outcome. For example, if there are three seats in the bus, and if A and B are the two persons are going to take the seats, and what is the probability that A will take the first seat? That is 1 by 3. Simply 1 by 3. And now, if second person goes, then what is the probability that he will take that second seat or third seat or whatever first seat? Then you can say that you can observe that these experiment, whenever the second person B is going, that is related, the probability or the uncertainty of taking the seats, or certainty taking the seats, is dependent, but A has already taken. So these are layman way to tell that what is mean by dependence. Mathematically, we are going to do. Of course, we have to handle mathematically everything. And independent event means if you throw a die, if you throw a coin, and for example, in throwing a die, six appears on the first throw, and on the second throw, what will appear? That doesn't depend what has come in the previous experiment. Okay, so these are the independent event, and before that we have to define the conditional probability. Okay, conditional probability means if if one event has occurred already, and how it will affect the upcoming events, how it will affect the probability of upcoming events, that is defined. Okay, so so this is the mathematical term that this omega, that omega fp is a probability space. That is probability space, and we want to define that if A and B are two events that is a subset of F, such that probability of A is strictly greater than zero. I'm not taking greater than equal to zero. By definition, it is greater than equal to zero, but I am taking here probability of A strictly greater than zero. Then I can define as probability of B given A. That is probability of A intersection B upon probability of. Yes, so I'm just defining it. I'm just defining it. Dependence, independence, how it is related to that layman approach. That is, it's just a curiosity that how that the things is related to these kinds of things. If you don't want to go those things, then you just stick on the definition, that what is the definition of dependent events. It's a conditional probability of B given. Okay, conditional probability of B given. Okay. Okay, so one important note is there. Okay, so we're going to define that. So this is a definition. Okay, definition you have to take it. And now the definition second is coming. That is exhaustive. Exhaustive events. Exhaustive events. It means that if you have sequence, or you can say subsets of A belongs to F, where I belongs to any index. What I mean by any index, it can be countable, finite, or uncountable, but every subset is belonging to F. And what is the probability? What is the property of these EI, such that probability of union, that I let's say I belonging to index. I will say I belong to index EI, that is equal to 1. This is the required condition. Then these EIs are exhaustive event. Exhaustive event. This is just a definition we will use. We are going to use this definition. For example, uh, this is this is your event space. This is your event space. If I say that this is the event, if I divide them as this is E1, this is E2, this is E3, this is E4, this is E5, this is E6, this is E7. So if I say that, then you can see that E1 union E2 union E7, that is giving you omega. That is giving you omega. If you try to oh, apply the probability on both sides, then this is probability of omega that is equal to 1. It means that E1, E2, E7 are the exhaustive events. These are the exhaustive events. Okay. Now let's see that. For example, if these are the exhaustive events, right? So if I say there is an event, um, so these are the events. This is an event that is happening. That is happening. Okay. So this is the event. Then and this red one. If I say this is the event E, okay, this is the E. Okay, so this is Venn diagram. You can say this is a Venn diagram. We have seen those Venn diagrams in the form of A, B, C on the circular and these kinds of stuff. And just to make you relate that this is the Venn diagram of the omega. And if you say that what is E, you can say that E is what? That this part, okay, that this part and this part, this part. If I say the union, then I can easily write as E as that E1 intersection E, right? This is union and this is E2, E2 intersection E. Okay, so this is union E7 is not coming. Okay, E6 is not coming in the event E. So E1, E2, E3, E4, E5. Okay, so if I write E is E intersection E6, that will be empty. There is no issue. Union. Okay, I just write every subsets, every partition you have taken, every part of that F, whatever you have taken. So you can say that this is the union of 1 to 7 EI intersection E, and you can see that every set, this set is disjoint. This set is disjoint, and they are mutually disjoint, or mutually exclusive. Mutually exclusive means they are disjoint and exhaustive events. These exhaustive events, E1, E2, E6, E7, though this E6 is not participating in this event, but still I can write it as I can write there is no harm. So then E, these are, what is the condition? That EIs are exhaustive, and the second is mutually ex, mutually exclusive. Mutually exclusive just means they are disjoint. Okay, so okay, disjoint means what? Disjoint, there are two kinds of disjoint, that is pairwise disjoint and three disjoint. So mutually exclusive means no matter how much collection you take, if you take 3, 4, 5, 6 or anything, they are mutually exclusive event. If you take any collection and their intersection is empty, then this is mutually exclusive. And pairwise disjoint means what? If you take from collection any two sets, and take their intersection, that will be empty. Now we are taking this probability of E, then I can write it as probability of EI intersection E, that will be equal to 1 to 7. So what is the probability of E? That this and this is known as total probability. This is known as total probability or total probability theorem, because this is a result. So I'm just giving respect to this theorem. So this is total probability theorem. Okay, so we are going to use it. Okay, so soon we'll do one or two questions. Okay, before that, an important. Okay, so before that, an important as well. Okay, so probability of E. Keep in mind that what we have taken here, probability of E. That probability of E is that some probability of E, I intersection E, and I is 1 to 7. Okay, I am just taking this 7 just to clarify the concept. Okay, whenever we will have a partition, it's not compulsory that it will have 7 parts. It may have 7, 8, 10, infinite and countable, always countable. We can assume that at this point of moment. Now, what we have done, that probability of what is the probability of EI? Suppose in the that probability of EI intersection E, that can be written as probability of E. Okay, so given E, given E. Okay, so from here I can write this, that probability of EI given E dot probability of E is. I'm just trying to relate the concept that we have done. Probably we will reach some good conclusion. So I am just you know writing this thing, that probability, or from here I can also write that what is the probability of E given EI. That is also simple, that probability of E intersection EI upon probability of EI, and from there I can write that this denominator part I'm taking to this left side, probability of EI, that is okay. So this part is what, this right hand side is what, this is simply this. So I am just replacing this part to this. So it's just an observation I am doing, like calculation. So let's see where. So that I is 1 to 7. I am just taking that particular example when I have the partition of 7 parts, right? So I can write this. So this I can also, this is also the same version. You're just writing that 5 equal to 5 or 5 equal to 2 plus 3. That is the same. It depends what's the requirement in the system. Okay, so this let's go to some some, okay. So if somebody asks um, what is the possibility or what is the probability that if event E has already occurred, and but that occurs in the okay, event E has already occurred, then what is the probability that it will occur from E4? Okay, in simple words. Okay, let's see mathematically first. We'll try to put in words. Hmm. Uh, that if somebody asks that what is the probability of EI, or say EI given E, what I have defined, that E has already occurred, and probability of E, that mathematically I can write it as probability of EI intersection
E
E and
over
probability of
probability
E.
of E.
Probability of E. Okay, probability of E, and E, that I am taking the same example. that I can write what I can write it as uh, probability of E probability of E given EI. Okay, I'm just using this definition, right? Probability of EI intersection E upon if I divide by probability of E, that is simply equals to probability of EI by E, and if I divide this probability of EI, that is simply that E, E upon EI. That is simple. Okay, that is simple. So these are just two forms that these are the product of the two numbers. I am taking one in the first denominator and in the second part I am taking the second one. So on the upper part, but which I am using this EI that which I am using. So this I am using. Okay. So this E I intersection F will be equal to probability of E probability of this that I have already defined that I can write it as no matter it will affect the probabilities or not, but I can write it as mathematically I am not wrong. And probability of E I have defined as that probability of E probability of E I intersection probability of E that you know. Earlier we have taken the example that 7. Okay, let's keep it 7 just to make the clarifying things. Okay, so uh, yes, and I'm using the value same. Okay, I'm using the value. Every part I can use as probability of E and probability of E given E I. Okay, so you keep remember that this is equal to 1 to 7. 1 to 7. If I do the partition of that set that I have that F, if I do the partition into n parts and I'm taking that countably
Excuse me, sir.
infinite or the yeah
Sir,
yeah
second step numerator, I didn't understand. Second step numerator.
okay
P of
this
E
right
into,
this one.
yeah, numerator.
Oh okay, sorry, numerator. Okay. So this you have in the numerator, right? P of E I intersection E, and this I write it as this. So what I have earlier defined, okay, I hope you recognize this probability of E lower probability of E given EI. It means that simply what I have defined here. So this is defined. This is defined, right? So what I can here, right? This is understood. Hmm? This is I can write it as probability of B given A, that is A intersection B, right? So if I just replace here by E and here by probability of what I have write is B as EI and A as E, then this is simple. A I replaced by E and this B is replaced by EI. I'm just replacing that events. I'm just using, I just define this conditional probability as whatever the event is from F, you can write two events as like this, as like this. Then I am just, multiplying denominator. I have two denominators, for example. So this I can write. Okay, I hope your doubt is clear.
Yes, sir.
Okay. So this I just write. Okay, this is just write, and this is just write. So we will use it. No, don't worry. I am just giving you the mathematical expressions. So whenever we will use in the questions, you don't feel, untouchable to the thing. So this is known as bias theorem. This is given by famous mathematician, that is bias theorem. Okay, so this this has wide applications, and in your exam it will surely appear because it's important and it's unavoidable part of mathematics and statistics that everybody has to take care of it. Okay. So this we will use. Okay, let's try some question from your. Okay, 35. We have 5 to 10 minutes. Okay, let me see. There are some questions. Okay, so okay, the question number. Let's see. Okay. Hmm. Okay, so let's try this question. If you have 2 points, a fair one with the okay. Okay, if you have 2 points, a fair one with the probability of head is 1 by 2 and an unfair one with probability of head 1 by 3, but otherwise look identical. A coin is selected at random and tossed, falling head up. How likely it is that it is the fair one? Okay, so it is the fair one. So if you see that you have a population like this of this is this is divided by two pairs, two two parts. What is this is fair and this is unfair. Okay, there are two coins that is you can say that put it on a table that has these kinds of boundaries, and you can choose any coin, and they are otherwise look identical. They are look identical, but they have different probability of getting heads. So whenever you are going to choose any one of the coin, they are identical, so they have equally likely probability of choosing. It means if you choose fair one, that have probability of choosing is 1 by 2. When you choose unfair coins, that have the same probability 1 by 2. So this has 1 by 2 probability, this has 1 by 2 probability, and both the cases head can appear, right? Head can appear. So I can say that this is the event. This is the event E. What is
Sir,
the event
unfair
E?
unfair is having 1/3
No,
probability.
okay. You have 2 coins. Okay, let me read the question again. You have 2 coins, a fair one with probability of head 1 by 2, and an unfair with probability of head 1 by 3. You have 2 coins. If you flip this coin, probability of getting head is 1 by 2. If you flip this coin, probability of getting head is 1 by 3. You have coin in your hand, then they look same. They look same. And when you have to toss, you can choose anyone. And when you are going to choose, you can choose this one or this one. They have the same probability of choosing. After choosing the coin, you are going to toss. Then the probability is different. Okay, so I hope this is understood that. But otherwise, look identical. A coin is selected at random and tossed. There are two things is going to happen. The coin is selected. First, we have to select the coin and randomly toss. Then we have to toss, and and they are asking how likely it is that it is the fair one. That that what is the probability that the coin was fair? Did you get my point? Okay, did you get my point that what I'm saying that there are two things we have to do. First, we have to select the coin and then the toss the coin.
Okay,
Selecting
whether
of them is yeah.
it may be a fair or unfair.
Yeah, it may be fair or unfair. It
Okay.
may be okay. For example, if I have two persons, A and B, and A person and B person, if I have to choose them and they are same for me, they are both unknown to me, the probability of choosing A and B is same, 1 by 2, 1 by 2. But when I choose any one of them, then I will say that then there is some, the difference is coming. That A will result something else, B will result something else. So choosing those, any one of them have the same probability. Okay, choosing any one of them has the same probability. So
Then it will be 1 by 2 only.
choosing any one of them, obviously 1 by 2. Okay, 1 by 2. So this is fair coin, this is unfair coin. Then let's, if E is the event, what is the event that head shows? Head shows. Okay, head shows. Okay, if E is the event and EI is the event that I even, let's say E1 be the event that fair one choose, fair one choose. I have to choose. Okay, E1 is the event fair one choose, E2 unfair choose, unfair choose. So simply you can say, if you try to apply that Bayes theorem, then they are probability, they are asking the probability if falling heads is going on. Head, what is the probability of head? That is E.
E.
Given EI, what is, how likely it is that it is the fair one? That fair coin is choosing, that they are
E1.
asking this E1. So simply we know that this is P of, okay, so P of
E.
EI.
E intersection E.
Okay, you can write it as well, but we have derived the formula from that
Yeah.
condition, that
P of
this
E
is
divided by
okay. So this is the thing. Okay, so I
summation
feel this is summation
P of
multi.
E.
Okay, so this is the thing. Okay. So if I do that, then what is the probability of EI? What is the probability of choosing?
1 by 2.
This is 1 by 2. Okay. So what is the probability of if E has happened? E, what is, head is coming, but head is coming from EI, E1, right? E1, E1. I have to write it E1. That E1, that E has happened. What is E? That head has shown. What is the probability that it is shown in
1 by 2.
E1? 1 by 2. 1 by 2. So this I is going from 1 to 2, right? I is going from 1 to 2. Then probability of E1, that is same, 1 by 2, 1 by 2, plus when I put I equals to 2, then probability of E2, that is same.
1 by
That
2.
what is 1 by 2. And if head has shown up, what is the probability that it's came from E2, that
1 by
E2,
3.
1 by 3, 1 by 3. So this is, okay, so I can cancel 1 by 2, 1 by 2, 1 by 2, and 1 by 2 multi, that will come, just the calculation. Okay, 5, and this is 3 by 5. Okay, so luckily this has answer as well. So this answer is coming up. Okay, so this is the application of the Bayes theorem. As simple as that. And let me conclude this session by one little bit, simpler definition. Okay. So, okay, so I will write here as well. So it's just a simple definition. If probability of A intersection B equals probability of A probability of B, then A and B are independent. This is definition. And you don't go by that how it is related to your real life, how it is related to, if you are confused, if you are clear with these concepts, that then you can ask, there is no doubt. But if you are confused, like how these are related to, like what are the example we have done, then you have to do some practice. Otherwise, don't it's not required to be confused in anything. You just go by definition. If anybody say what is the meaning of independent of two events, you say just if the probability of A intersection B equals to product of their individual probability, then they both are independent. That's the only basic or the fundamental thing you have to keep in your mind. Okay, so one question we will do and we terminate this. Okay, so 81. Okay, so this is the thing. Okay, so this one question we will do. This 81 we will do. And okay, so if A1 and A2 are two events such that the probability of A1 union A2 is this probability of A1 plus probability of A2, then when okay, so let me clear the question. If A1 and A2 are two events, then this is given when they are asking the condition if A1 and A2 are independent, A1 and A2 are mutually exclusive, A1 is contained in A2, A2 is contained in A1. So we know that this probability of A1 union A2 is equals probability of A1 plus probability of A2 minus probability of A1
A intersection from A1 intersection A2.
A1 intersection A2. If this is given, it means what? But when it
That
will
is
happen?
0. Only when they are
That
mutually exclusive.
that will be 0. So they are mutually exclusive. They are mutually exclusive. But you have to give you should keep in mind that you have the example like why they are false. This is true, but we have information. I know that this is true. Why they are false? Okay, why they are false? You should have and some example in your head, right? For example, if you take as A1, okay, if you take A1 as subset of A2, huh? Okay,
Then there, when we take the intersection, there are some elements which are both in A1 and A2.
okay, huh? Then it will be not there, right? Then probability of if I will say that A1 subset of A2, then probability of A1 intersection A2 will not be 0, right? It, it will not be 0. If A1 is contained in A2, then it will not be 0. Then this conclusion will not hold. So this option is false. Similarly, we can false this conclusion. So what about this option A? If A1 and A2 are independent, what is mean by A1 and A2 are independent? That A1
and P of A intersection B is equal to
Probability of A into probability of B. A2.
so this is the only thing. Is this implying that probability of A1 union? This is a question. Is this implying that A1 A2 that is equals to A1 plus probability of A2? No, it is not implying. It is not implying. Why? Because you just required an event where probability of A1 intersection A2 is not equals to 5, right? Not equals to
Yes,
5.
sir.
You just required that. So tomorrow you have to give me an example of an experiment or okay data where A1 A2 is independent, but their intersection probability is not 0. Okay, so for this option, okay, I understand that this is false. This is false, and most of the students will follow that. But if it is true, we don't know that it is true or not. We just okay. So you have to give me an example tomorrow. So let's finish this class today. Any doubt you have?
No, sir.
Okay, then I hope you are understanding. Okay, are you getting what I'm saying or what I'm trying to say, you guys?
Yes, sir.
Sir, while
Okay,
explaining the concept, if you give the example and clearing, then it will be more easy for us to understand, sir.
okay, then I will do that. I will do that. I will share, PDF of the notes as well. So I just to to make less time on understanding because we have to cover a very much. I cannot, explain every example because I understand that examples are important.
Not
But I
like that.
suggest
What
you.
I am telling
Ah,
is
okay, okay. Then I
mutually
will try
exclusive.
it. Okay,
What
okay.
is
I will try it.
mutually exclusive, what does it means? For example, if you take an example and tell,
Oh, okay. That I will take care. That I will take care. Okay. So I will send these notes as well, and they have bunch of examples. You just go through it. If you feel any doubt, just feel free to connect. Huh? Feel free to connect. Tomorrow we will continue our class and we'll try to do much more.
okay,
Okay.
sir. Okay, sir. Thank you.
Okay then. Good. Okay. Bye.